Well, good morning, everyone. This is video number 2. I think you're going to like this better than video number 1. Video number 1 with graphing has some detail that makes the problems take a lot longer. So today we're learning a faster way for finding the solution to a system of equations. We're going to do 5 examples today, and the assignment that I'll give you has 20. So this is our next goal. Substitution is called a power standard. It's used in some form or fashion in every math class all the way through high school. So it's good that we're spending at least a full day on just the substitution technique. It's, once again, called a power standard. So we can't skip it. We've got to be good at it. So we're starting easy, and we're going to kind of go to medium, and then I'll do a more challenging problem as our 5th example. So starting on the left side, example 1, our system is x equals -4, and we also have the line 2x plus y equals 7. Hopefully you remember that this is a vertical line, and this is not a vertical line. But we're going to use algebra to find where these two lines intersect. I want to remind everybody that the solution to a system is an ordered pair. So I already know half of the ordered pair. It says x must equal -4. So that tells me that I already know my x coordinate. This problem is inherently easier than most because they're giving us the x coordinate already before we even begin. So hopefully you can see why this process is called substitution. We're going to take this value of -4 and we're going to substitute it in for x. We're going to replace x in the other equation with -4. When I do that, the work should look something like this. 2 times -4 in parentheses plus y equals 7. You can see that this equation only has one variable now. That's the point. When we make a substitution, something good happens. We now have the equation -8 plus y equals 7. And now if I want to isolate y, get y by itself, of course we'll add 8 to both sides, and lo and behold we get y equals 15. So notice my solution that was half done can now be fully done by plugging in 15 for my y value, and I'm just going to box my final answer. I also want at this time to remind you that you can check your solutions if you have Desmos open. You could type in x equals -4 on one line, you could type in 2x plus y equals 7 on another line, and you'll see the two graphs intersecting at the point -4, 15. Don't just use Desmos to get answers because this algebra is what you're going to be graded on at some point. This is a great way to check answers and to remind yourself of what these graphs look like. Okay, we're going to go a little bit faster now. On example 2, we certainly don't know the x value, but aren't they giving us the y value? So this is another kind of simple one. We know the y-intercept right away is 5, so I'm putting it in the y position, not the x position, right? You gotta make sure you get your x's and y's in the right spot. They always go in alphabetical order, x then y. So now comes the substitution. I know that y is 5, so I'm taking this value and plugging it in for y in equation 1. Equation 1 becomes 3x plus 2 times 5 equals 18. Now we have 3x plus 10 equals 18. In our attempt to get x by itself, I'm going to subtract 10 from both sides. When I do, the 10 and -10 drop out, giving me 3x equaling 8. And now I'm left with that last step of division. Divide both sides by 3. We're getting x equals 8/3. All right, this is not a whole number. I'll be honest, on the homework, I believe every question will have whole numbers for x and y. But I wanted to give an example where we get an x value that isn't a whole number, because imagine trying to find the solution using the graphing technique we already learned. It just simply would be too difficult to get a more precise solution like this if we use graphing every time. So we can see one of the purposes of substitution is it allows us to get accurate answers for systems whose solutions are trickier than the ones that we would have if we're just graphing. So once again, I'm going to take this value, I'm plugging it in for x, so I'm listing my final answer as a point. 8/3, 5. Some people might be uncomfortable leaving the answer that way. You can turn this into an improper fraction, although it isn't necessary. That should give us 2 2/3, 5. If you're unsure about an answer like this, once again, you can type both of them into Desmos, and you will see that that is the intersection point. Okay, example 3. We're looking a little bit different now. We have a's and b's instead of x's and y's. But shouldn't the algebra be the same? So I won't ask you to graph in this way, but the reason I'm changing variables is we're going to be working with word problems soon. And we won't always have x's and y's. We might have c's and d's, or a's and b's in this case. So let's not let the changing of variables bother us. Notice that we have an expression for a. It's equal to 3b, isn't it? We don't know the value of a, but if I make a substitution into the second equation, in other words, if I replace a with what it's equal to, which is 3b, we get an equation that's going to work out nicely. So once again, I'm substituting what a is equal to in for a, and that gives me 3b plus another b equaling 84. Okay, the numbers are a little bit bigger here, but solving it should be easy. 3b plus b is 4b. And so now I know 4b is equal to 84, so I can see that our b value is going to spill out pretty quickly here, right? Divide both sides by 4. I'm getting a b value of 21. 4 goes into 84 21 times. Okay, so are we done with this problem? Think about it. We are trying to find not an XY combination, but an A, B combination, right? And which value did we find first this time? The B value, right? So A must go here, B must go here. So hopefully everybody can see that we know that the second coordinate must be 21. Okay, so how to find that first coordinate? Well, just look at this top equation. It already has A isolated, doesn't it? So therefore, I can use that top equation. A must equal 3 times whatever B is, but we just found out that B was 21. So hence, if I just plug in 21 there, I have A all by itself, and 3 times 21, I believe, is 63. So once again, the numbers are a little bit bigger this time, but that shouldn't make any difference. If I plug in 63 for A and I plug in 21 for B, notice they do add up to 84. So it does satisfy equation 2, and it definitely satisfies equation 1. Okay, now for 2 more that are a little bit trickier. I'm going to need to erase for a moment, so please excuse me while I do that. But example 4 and 5 are coming right now. All right, the equations are obviously looking a little bit fancier. Notice that this problem is set up nicely for substitution, and it's set up nicely for substitution because notice that y is already isolated in the second equation. So I'm just going to remind everybody that y is equal to something that has 2 terms. These are called binomials. So I'm going to take that binomial and I'm going to put parentheses around it. This is what we do with algebra when we make substitutions like this. So since I know that y is equal to this stuff, 2x plus 3, I'm going to replace y with 2x plus 3 into the top equation. This is tricky because if you forget the parentheses, it will give you the incorrect answer. So our top equation, going slowly here, is 3x minus, and now we're replacing y with 2x plus 3. Notice it needs to be in parentheses. That grand total, it says, must equal negative 2. So notice after we make the substitution step, we have only one variable, right? That's called progress in math. So if I'm going to solve this problem now, I need to remove the parentheses by distributing a number in front of it. The number in front of it is actually negative 1 because there's an invisible 1 that's right there. So I'll draw it in to make sure everybody knows. We're going to be distributing this number to this parentheses, and now you can see why I gave you all those distributive property problems on the last page of your first assignment. It's one of the important skills for using substitution in algebra. So to complete this problem, I'm going to distribute negative 1, and when you do, the parentheses are going away. So I have 3x minus 2x, and then minus 3 because the negative 1 distributes to both of those terms. Don't forget to copy the right side of your equation. So here we are, we've almost got x by itself. 3x minus 2x is 1x, or just x. And then minus 3 equals negative 2. So we've almost got our x value. So to get x by itself, I could just add 3 now to both sides. So I'm finally learning that x is equal to 1. Don't be a student that stops here and say, oh, I'm done, I found x. When you're working with systems, you're only half done once you find your first value. So here we know this point of intersection has to be 1 comma something, right? 1 comma something. And that y value is going to spill out to us if we just plug it in to one of the equations up top. Let's think about which equation is going to work best. Can you see the second equation is going to work really well for solving for y? Because the y is by itself, right? That's what we want. We want this equation because it will output y for us so easily. So over here, I'm going to recopy equation 2, y equals, and I'm simply going to plug the value that we already know for x in for x. And that's 2 times 1 plus 3. You can see why equation 2 is working so nicely for finding the y value. Of course, the y value just simply needs to be 2 plus 3, which of course gives us y equals 5. And once again, we are finishing off and giving all of our solutions as an ordered pair, because that demonstrates that you know what we're doing. We're finding a point of intersection. All right, are you ready for number 5, the most challenging one of them all? So problem 5, let's see, negative 2c plus d equals 14. And our second equation is c plus 2d equals 8. So this is a challenging looking problem because notice that both of our equations are in standard form. All the problems up until now, we've always had one of the variables isolated already. And in this problem, neither variable is isolated. So I have a choice. As I look, I need to get this equation or this equation solved for a single variable. It's best to search for a variable that has a coefficient of 1. And what I mean by that is the number in front of the variable is a 1. The coefficient of c here is negative 2. So getting c by itself will be ugly. You'll have fractions. But getting d by itself in equation 1 would work beautifully, because notice the number in front of d is a 1. So solving the first equation for d works nicely. I could also solve the second equation for c, because notice that its coefficient is equal to 1. Since this problem is trickier, I'm going to number the equations so I can keep track of them and demonstrate the substitution step very nicely and make it as clear as I can. I'm going to rewrite equation 1 by isolating d. Getting D by itself involves me adding 2C to both sides of this equation. So our top equation with D all by itself is going to be D equals, and now the expression on the right is 2C plus 14. If you write 14 plus 2C, that should give you the same answer. Okay, so now I know that D is equal to this stuff, which I'm going to put a little squiggly circle around. The substitution has to go to the other equation. Notice that this is equation 1. The substitution must go into equation 2. So now I'm simply recopying equation 2, but with D replaced with 2C plus 4. Notice we're going to be using parentheses again. So you need to think of this as two terms. And so as we copy equation 2, here we go. We're going to have C plus 2, and now is coming D. But D has two terms, so it has to be in parentheses, which gives us 2C plus 14. The total on the right side, to keep our equation intact, is an 8, isn't it? So notice this problem's a little bit trickier, but we only have one variable in this equation, right? So good things should happen. So let's distribute the 2 and see what we get. This is C plus 2 times 2C is 4C. 2 times 14 is 28. So be careful with your distributing. And that total on the right is 8. I see some like terms here. 1C plus 4C is 5C. Plus 28 equals 8. We're getting there. To get C by itself, I should first get 5C by itself. So I'm going to subtract 28 from both sides. This gives us 5C equals negative 20. Okay, we've almost got our first variable, right? If I just divide both sides by 5 now, notice C equals negative 4. Finally, that's most of the work. Most of the work is done. We know our solution is going to be negative 4 comma something else, but we still need to know what D is, don't we? And once again, I can use either of the equations on top, but let's think about this. If I want to know what D is, doesn't equation 1 in this form where D is by itself going to work the best for that? So I'm just going to go just to the right here, and we're going to write D must equal 2C plus 4, but I know the C value is negative 4, so this equation is just perfect. I have my 2, the C value is negative 4, notice the parentheses, plus 14, plus 14. So we're almost done with this problem. We have D equals negative 8 plus 14, and negative 8 plus 14 is 6, I think. So therefore, it looks like these two lines are intersecting at the point negative 4, 6. Hopefully this helps you with your 20 problems. That is assignment number 2. And please continue to email me if you have questions.